Welcome to Video Help with Physics Problems for Physics 1B. This video is going to cover Homework Set 3, Part 2, which is everything under the headings Faraday's Law of Induction and Inductance and Magnetic Materials. For 1221, this will cover questions 8 to 13, and for 1231, this will cover questions 10 to 17. This is Problem 8. For 1221 or 10 for 1231. In this problem, we have two loops of wire that have a common axis, a large one and a small one. They're separated by a distance d, and along here is their common axis. We're told that a clockwise current is suddenly set up in the larger loop, so it goes around like that, clockwise current. And in part A, we're asked what is the direction of the induced current in the smaller loop? Well, we could immediately say that it's anti-clockwise, as it must oppose the change that induces it. But it would be better to consider the induced magnetic fields, because that's how the signal is going to travel from this larger one to this smaller one. So let's draw on the magnetic fields and the induced magnetic field. When we start up a loop, when we set up a clockwise current in the large loop, it generates a magnetic field going along the axis, but in the negative direction like this. So we can see we're going to have a south pole here and the north pole over here. So this magnetic field induces a magnetic field to oppose this one. So if it opposes it, we must have a south pole here and a north pole here. So a magnetic field like this. So to get a magnetic field like this, we're going to have an induced current which goes in the anti-clockwise direction, like that. So that's a more thorough answer. Now part B asks, what is the direction of the force, if any, that acts on the smaller loop? Well, you can see that we've got a south pole here and a south pole here, so we've got opposing magnetic fields. So that tells you that they're going to feel a force away from each other. So force directed away from larger loop. Now this magnetic field's only going to be induced just when this one starts off. It's only a changing magnetic field which will induce a magnetic field. So this force isn't going to be sustained, it's just going to feel a force, and then that's going to disappear as the current becomes established. Problem 9 for 1221 or 11 for 1231. In this problem, we've got a setup where we've got a solenoid wrapped around a piece of metal. Now before we add the resistor onto this diagram, let's just consider what happens to the magnetic field when this switch is shut. As soon as this switch is shut, we get a current flowing through our wire like this. And so you can see that's going to have a magnetic field induced, and the magnetic field will have a north pole up here and a south pole down here. Now let's consider our resistor. We have a resistor down here like this. And we're asked about the direction of flow of current through this resistor. Now immediately after this switch is closed, we're going to have an induced magnetic field in this red wire here, which will oppose this one. So we'll end up with a north pole induced here and a south pole induced here. This is only immediately after the switch is closed. So for that to happen, we must have the current flowing this way. So the current is flowing from the right to the left. So A, from the right Part B asks sometimes after the switch S was closed. Well, after the switch is closed, there's a steady magnetic field. It's only changes in the magnetic field that induce current to flow. And so there will be no current when that magnetic field is not changing. Now, part C says immediately after switch S is opened. So in that case, the current will be induced in the opposite direction, as this south pole will be getting less strong, so we'll have an induced south pole here, an induced north pole here to oppose that change. So this will be from left to right. And part D says when switch S is held closed, which end of the coil acts as the north pole? Well, we've shown it's the left end. You can do that with just your right hand rule. Problem 10 for 1221 or 12 for 1231. In this problem we have a couple of metal rails, so these will conduct electricity. They're 50 centimeters apart, and we've got the point D here and the point C here, and these are joined by a wire. And then we've got another bar sliding along these rails in this direction. We're told the velocity is 8 meters per second. And this here is our point B, and here is our point A. We've got a magnetic field going into the page. It's a uniform magnetic field, and the strength of this magnetic field is equal to 1.0 Teslas. Now we're told that the resistance of A, B, C, D is equal to 0.4 ohms. We're assuming this is constant, which is a big assumption as we're changing the length of AD and BC. So part A asks what EMF is induced in this rod here. So we'll need to use our formula that the induced EMF is equal to minus d phi b dt. Now phi b is equal to BA. In this case we've got a constant magnetic field, so this part, the B, is not changing with time. It's the area which is changing. If we consider this as our x direction and this as our y direction, then we've got this is equal to BXY. And you can see it's the x direction which is changing with time. Y is fixed at 60 centimeters. So substituting this into here, we can write EMF is equal to minus. Now B and Y are constant, not affected by time, so we can pull those out the front of this derivative. And then we've got dx dt. Now we know dx dt, that's just the velocity of the rod along this way. That is telling us how much x is changing. So this is equal to minus BYV. So now we can substitute in. We've got minus 1.0 times 0.50 times 8.0. On the diagram, this dx dt is moving in the negative direction, so we can cancel out this negative, and we end up with 4.0 volts is induced. Part B says what force is required to keep the rod in motion. Well, to do this, we're going to need to think about the induced current. So the induced current must oppose the change that induces it. So this BA is what's changing. Our area is increasing, so phi is increasing. So for to oppose that increase in phi, we need the induced current to decrease phi. So the induced magnetic field must oppose this applied magnetic field. So our induced magnetic field will be coming up out of the page. So B induced out of page. So to get an induced magnetic field out of the page, we need an induced current flowing like this, anti-clockwise through our wire. Now we can calculate the size of this induced current using V is equal to IR. This is our induced EMF, which is our induced voltage here. So we have I is equal to V over R, so that's the 4.0, and we're told that the resistance is 0.40 ohms, so this is equal to 10 amps. And so the size of the force is given by I, L cross B. And this induced current has a size 10. We're considering the force on the rod. So the length of the rod is 50 centimeters, so 0.50 meters. And then B, the magnetic field is not the induced magnetic field, it's the applied magnetic field, which is the 1 Tesla, is at right angles to this rod. So we have 1 times 1.0. Solving that, we end up with 4.0 newtons. And the induced force, F induced, is going to be to the right, just from this cross product. We can see that clearly it's going to oppose this velocity. But in the question, we're not asked about this induced force. We're asked what force is required to keep it in motion. So to keep it going at a constant velocity, we need to apply a force equal to this induced force and in the opposite direction. So the applied force will be 5.0 newtons to the left. So in the same direction as this velocity here. Now part C says compare the rate at which mechanical work is done by the force with the rate of development of heat in the circuit. So dW dt, using the mechanical force, this is equal to dF dot ds. The force isn't changing with time, we're applying a constant force to keep it going at a constant velocity. So this is equal to Fv, because the change in the distance with time is the velocity, and so this is equal to 5.0 times 8.0, which is equal to 40 watts. The rate of development of heat, we can use P is equal to Vi. We've said that V is 4.0 and that the current is 10 amps, so this is equal to 40 watts as well. So they're the same. So the mechanical power is going into the electrical power. Problem 13. This is 1, 2, 3, 1 only. In this problem, we've got a loop of wire. It's being turned in a constant magnetic field, B. Here we've got a length little b, here's length little a, and we'll assume that it rotates at a frequency f. And we're asked what's the induced EMF. Now the induced EMF is equal to minus n, the number of turns, times d phi b dt. We'll need to have a bit of a look at this phi b. Phi b is equal to b dot a. Now the direction A, we take the direction as perpendicular to this plane here. So it's coming up out of the page. So as this turns, the angle between A and B is going to change, and that's going to be related to the frequency at which they're turning. So how we can write this, B is constant, so it's B. We've got this area is AB, but then because of this dot product, we've got the cos 2 pi ft to describe the angle between the area and the magnetic field. So now we can substitute this in here to work out what our EMF is going to be. So our EMF will be equal to minus n d ba b cos 2 pi ft dt. And so this is equal to minus n b a b. When we take the derivative of this, we get 2 pi f, and then that'll be sine 2 pi ft. Now, if we let maximum EMF equal epsilon naught, then we can write this as epsilon naught sine 2 pi ft. Sorry, you shouldn't have the negative here. This negative cancels out with the negative from the derivative of cos. So that's our answer to part A. Part B says design a loop that will produce an EMF. So the maximum EMF is equal to 150 volts. So we have 150 is equal to NBAB times 2 pi f. And we're told that it's rotated at 60 revolutions per second. So the frequency is equal to 60. The magnetic field strength is equal to 0.5 Teslas. Okay, so just substituting in little a, little b is equal to capital A. So we have NA is equal to 150 divided by B, which is the 0.5, and then divided by 2 pi and divided by the frequency. So solving this, we end up with 5 over 2 pi. And we can't say anything about n or a. These are dependent on each other. If a is bigger, n can be smaller. And if n's bigger, then a can be smaller. So this is turns meters squared. This is problem 11 for 1221 or 14 for 1231. In this problem, we've got a solenoid which is wound from insulating wire. So it's wound so that the wires are right up next to each other like this. And we're told that the diameter of the copper is equal to 2.52 millimeters, and that our solenoid is 2 meters long, and that it has a diameter of 4.10 centimeters. So the radius in that case will be 0.0205 meters. Now we're asked, what is the inductance per meter at the solenoid near its center? So we'll need to use the formula for inductance. L is equal to N phi B over I. We're now going to need to use this information to work out what these things are. So N, that is the total number of turns. So that will be equal to the length, which is the 2.0, divided by the thickness of each turn, which is the 2.52 millimeters. So 2.52 times 10 to the minus 3. So solving that, we get that N is equal to 794 turns. Now we'll need to work out phi B. So phi B is equal to BA. B, because this is a solenoid, we've got mu naught Ni, and A, that's our surface area, that's our cross-sectional area here, which is the pi r squared. So we've worked out r here. We can't work out I at this stage. N, this is the number of turns per meter. So this will be equal to mu naught. Now N will be capital N, and this is 2 meters long. So it'll be 794 divided by 2, which will be 397 times I times pi times r squared, which is the 0.0205 squared. Okay, and then over I. So let's substitute these in and see what we end up with. So we've got 794 times mu naught times 397 times I times pi times 0.0205 squared all over I. So it's lucky for us these i's cancel, as we couldn't work out what they were. So now everything here is a number. Mu naught, remember, is just 4 pi times 10 to the minus 7. So you can solve this on the calculator and you end up with 5.23 times 10 to the minus 4 henries. Now going back to the question, it wasn't actually asking for the inductance, it was asking for the inductance per metre. So this is the inductance over 2 metres. We just need to divide this by 2 to get the inductance per metre. So L per metre is equal to a half of this, which is 2.61 times 10 to the minus 4 henries per metre, or we could write this as 261 microhenries per metre. We're now up to problem 12 for 1221, or 15 for 1231. So in this problem we've got a solenoid. The number of turns is 1870. The length of the solenoid is equal to 1.26 meters, and it has a current of 4.36 amps, and its core is filled with a material with an effective permeability of 968, which tells us that mu of the core is equal to 968 times mu naught. The diameter of this solenoid is 5.45 centimeters, so that tells us that the radius is equal to 0.02725 meters. Now we're asked to calculate the inductance of the solenoid. So to do that, we'll use the formula L is equal to N phi B over I. We know what I is, we know what N is because we're told these things, so what we need to do is consider phi B. So phi B is equal to BA. This is a solenoid, so the magnetic field inside the solenoid is given by mu Ni, and the area is pi r squared. So mu, that's 968 mu naught, times N. Now this is the number of turns per metre, so that's 1870 over 1.26. The current is 4.36, and we times it by pi r squared. So solving this, we end up with this is equal to 0.01836, and now all we need to do is substitute into here. So we've got 1870 times 0.01836 over this current, which is the 4.36. Solving that on the calculator, we get 7.87 henries. So that's how we do that one. Okay, problem 16. This is for 1231 only. First of all, we're asked to consider two inductors in series. So we've got series circuit like this. Here's L1, here's L2. Now, as they're in series, we know that they have the same current. And we know that V1 plus V2 will be equal to the total voltage. And we're asked to show what the equivalent inductance is. So for this one, we'll need to use that the EMF across inductor 1 is equal to minus L1 di1 dt. So this is equal to minus L1 di dt, because the current's the same everywhere, as this is a series circuit. And the voltage drop across inductor 2 is given by minus L2 di dt. Now in series, we've written this, which tells us E1 epsilon 1 plus epsilon 2 is equal to the total, and so we've got the total EMF is equal to minus L1 di dt minus L2 di dt, which is equal to minus L1 plus L2 di dt. So the total EMF, we can write that as minus L total di dt. These cancel, and you can see that the total, the equivalent inductance, is equal to L1 plus L2. So we've shown that relationship now. And part 2 of part A says, why must their separation be large? Why must this one and this one be separated by a big distance? It's because if we have a change in current in this one, it is going to create a magnetic field, a changing magnetic field, which will induce a current in this one, and we want to ignore that induced current. So as long as these are separated by a large distance, then we can ignore that induced current as it will be small. Okay, part B, we're now asked to a similar question, except that now our inductors are in parallel. So we've got L1 and L2. And our rules for parallel tell us that epsilon 1 is equal to epsilon 2, and that I1 plus I2 is equal to the total current flowing through here. Okay, so our total induced EMF in this case will be minus L1 di1 dt, which is the same as minus L2 di2 dt, which we can write as minus L total di total dt as well, if we're trying to find our equivalent inductance. Now, di total dt, we've said that this is I1 plus I2. So let's just write this over here. We've got minus L total di total dt is equal to minus L total di1 dt plus di2 dt. And this, we've said, is equal to the total EMF. And just rearranging this part of this equation, we can replace this di1 dt with epsilon total over minus L1. So we can write this as equal to minus L total di1, which is epsilon total over L1. That's a minus, and this will be minus epsilon total over L2. And this is equal to the epsilon total. So these epsilon totals now cancel out, and we can write this as 1 over L total is equal to 1 over L1 plus 1 over L2, which is the expression that we were trying to get. So we've now shown that. Now once again it asks why must the separation be big, and it's the same because if we have a changing magnetic field induced here, unless that separation is big, that changing magnetic field will induce a current here, which will change this result a little bit. Okay, and problem 13 for 1221 or 17 for 1231. In this problem, we're told that we've got stored energy of 25.3 millijoules, and we've got a current of 62.0 milliamps. In part A, we're asked to calculate the inductance. So this is the magnetic energy. We've got the formula for magnetic energy. U is equal to a half Li squared. So we can just rearrange this so that we've got L is equal to 2U over I squared. And now all we need to do is simply substitute in. So this is 2 times 25.3 times 10 to the minus 3 over 62 times 10 to the minus 3 squared. And solving that on the calculator, we end up with 13.2, and it's inductance, so it's in henries. Now part B says what current is required for the magnetic energy to be 4 times as much. Well, we could just multiply this by 4 and then solve it to work it out, but a faster way to do it is if we want this to be 4 times, because this is a squared relationship, if we double the current, then we'll end up with 2I squared, or 2I all squared, or 4I squared. So we just need to double the current. So double the current, which tells you that I will be 62 times 2, so 124 milliamps. And that's the end of this problem set.